one last speaker tonight, and earlier Tony mentioned that Department of Energy is doing some of the funding for the LSFP. So we have today a bureaucrat from the Department of Energy with us, Anže, Slosar, who's going to give an incredibly bureaucratic talk. So he's going to tell us a little bit about the origins, not just of human life or of the Earth, but of the universe itself, where it came from, and why it doesn't make sense for it to be existing. So here you go, Anže, Slosar.
This is actually surprisingly stressful because I used to give public talks and I get a lot of public talks, but this is like stand-up comedy, so I'm supposed to give the menu and you're supposed to give me feedback, but in a way I'm really supposed to like put you in free, so what you're supposed to like do rather than laugh. So basically, I'm a cosmologist, so what I do as a cosmologist, I try to study the universe as a whole, basically. What is it made of, how it got started, how fast it expands, how it will end, all big questions that keep you awake at night, until you get a permanent job as a professor and then you can sleep again. Actually, a lot of these public talks, I have two questions that people always ask me. First question is, what does the universe expand into? And second question is, what was there before the Big Bang? Okay? I'm going to talk a little bit about the second question, but what I really want to tell you is a nice anecdote about a nice paradox of theoretical physics that goes and the Boltzmann paradox. I hope it will blow this Boltzmann brain, its name was paradox, and I hope it will blow your brain. Okay? So let me start with the fact that symmetries in the universe are very, very important. Okay? So we like having symmetries. And they're kind of the guiding principle of how you do theoretical physics. Okay, so if you write down the symmetries of a given physical system, you can essentially work out basically the properties of this system. For example, the fact that energy is conserved is simply a property of the fact that time is the same everywhere. So this didn't used to be like this all the time. For example, in the medieval Earth, people believe that like up and down is a special direction. It's different from like left and right, and forwards and backwards because things go down. Okay. Now we know that up and down is not really a special direction. It's just kind of the fact that we have this piece of rock. So if somebody removed the Earth, up and down would be the same as left and right and backwards and forwards. And by the 19th century, people already worked out the importance of the symmetries, and that the symmetries can teach us that having symmetries is good because it is the right theory, and the theory is good. Okay? So at the time they didn't know the universe expands, so they thought that the universe must be. They tried to think of the most symmetric way of like writing the theory of the universe. Okay? So they knew about the motions of the planets and so on. They knew the basic Newtonian physics, but they didn't know essentially the universe expands. So the most symmetric theory of the universe is that it's both the same everywhere in space, right? But it's also the same everywhere in time. Okay? The universe now is the same as the universe a billion years before, or universe a billion years later. Okay? And they thought, okay, this is great. We can think of the universe. They didn't know about galaxies, they knew about stars, so they said, okay, the universe is uniformly filled with stars, and it's the same all the time. Okay? It just doesn't change. Okay? It doesn't expand, it doesn't try to see. Okay? And there are a lot of conceptual problems in the universe that doesn't change with time. And I'll explain now why we have this. So the first, to talk about this, let's talk about the concept called entropy. And entropy is simply the fact that basically, once your car runs out of gas, it stops running. Okay? And you think, in the first beginning physics class, they teach you about conservation of energy. You have one pool ball hitting another pool ball, and then you conserve, and the pool balls keep on moving. But once you run out of the gas, where did this energy go? It doesn't seem to be conserved. You need to pay $1 trillion to get your car moving again. Okay? And this is because this energy hasn't really been lost. It's just been converted into useless energy. Okay? So you put your gas into your car moves, but then you break it, you convert it to heat, so you can heat a little bit of air. So this energy is kind of now spread all over the Earth, but you can't use it. You know? So you turn useful energy into useless energy, and this goes in the name of increase of energy. Okay, and it's kind of sad, right? And the same thing happens if you say if you take like the bowl and you feed it like half with salt, half with pepper, salt on the left, pepper on the right, and you mix it. You get like a nice gray mix, and you can try to mix it back, and nothing will happen. Okay? So you cannot mix it. You can mix it backwards and forwards as much as you can. Basically, once you screw it up, you screw it up. Okay? So this defines clearly that things go from more ordered things to less ordered things, and there is a clear change which you call increase. And that's the biggest problem with kind of infinitely old universe. If you have infinitely old universe, you know, it will kind of use all its fuel in a finite amount of time, but because it's infinitely old, this happens in infinite past. Okay? So it doesn't make any sense to have a universe like if you have entropy increasing, right? And if the universe is infinitely old, it must increase its maximum in the past infinity. Okay? It's kind of crazy, you know. So universe that has no external input of kind of new energy will just be this maximally mixed up state where everything is the same. There's no more fuel. All the stars are dead, and it's like this for infinity. Okay? And this is bothering Boltzmann, right? Because this thing doesn't make sense. Like if you look around, you see now our Earth and so on. You still see things changing. We can drive cars. If you have this class, I can throw it to the floor. It breaks down. So Boltzmann, which is a famous physicist in the 19th century, tried to think of a way around it, okay? And then the idea came out, it's kind of crazy. He said, okay, if the universe is infinitely old, right, it's also infinitely patient, okay? So infinitely unlikely things can happen to the universe at this infinity, right? One thing that can happen is that if I throw, let's go back to salt and pepper thing, right? So if I have like salt and pepper, salt on the left, pepper on the right, I mix it and I get a mix. I try to mix it back and I get still a mix, right? But the idea is if I mix it back forever and ever and ever, really infinite amount of time, sooner or later, if I have infinite amount of time and I'm infinitely patient, right, things will unmix by chance, by pure chance. You get salt on the left, pepper on the right, and pure down. Okay? So things that don't normally happen can happen with very, very, very unlikely fluctuations. Okay? So Boltzmann idea is the following, right? So we have this universe which is infinitely old and it has used up all its fuel, but if I just sit there and wait and wait and wait forever, sooner or later, basically you get this random fluctuation where the universe pops up, you get sun and earth and dinosaurs and blah blah blah, and you wait and you get Boltzmann, and he can think about it, right? And because he can think about it, he knows it's here, so this story must be the right thing. Okay? Sounds kind of crazy, okay? So, but then, like a nice analogy is the following. You mentioned what I call evil casino, right? So evil casino is casino when you go in, and you only get out. So you go to evil casino, you go in, you can't get out. There is a crazy evil manager that tells you, okay, you throw the dice 100 times, and if you throw number 6 50 times, they'll let you out. Okay? So if you wait outside this casino, you see a guy coming out, and you say, okay, how many times did you throw number 6? 50 times in a row. You think this is pretty crazy, right? But because he managed to get out, you know, he couldn't have gotten out unless he done this systematic thing. So this same thing with Boltzmann brain. The fact that he exists means that this extremely unlikely thing didn't happen. But there is another problem, right? And the problem is that even if you buy the story with something crazy, and it's both realized it's kind of crazy, is that you don't need all complexity, right? So if you get the random guy coming out of our evil casino and you ask him, did you throw the number 6 7 times in a row? He said, well, hell no, I threw it 50, maybe 51, maybe 2, but just enough to get out, right? It's unlikely that somebody will throw 50 times and then 20 times more just for fun, right? So the equivalent thing here is that instead of creating the Earth, the dinosaurs, the sun, and moon, and so on, the much more likely thing is that you will create the minimum amount of consciousness in order to realize that this is the right expression of the universe. Okay? So Boltzmann thought, what is really the most logical thing is that instead of creating everything, you just create kind of this brain, with kind of enough physics knowledge, to work out what's the reason for existence of the universe, the brain itself is a wave of iteration, then die away. Right? And this is what the name Boltzmann brings, right? And the fact that Boltzmann saw all these stars and Earth and Sun means that this story is too unlikely, right? It's much more likely to appear as just a brain, nothing else than the Earth. So Boltzmann, this sounds pretty crazy because it is. So it was clear at the time that this is crazy, crazy explanation, and that the universe cannot be infinitely open. Okay? Because of this entity, we have used all the fuel in it. Luckily, however, there's another way out, which was popular in the 60s. Okay? Now this is less crazy than Boltzmann. So in the 60s, people had this other theory, which is called steady state theory. So by the 1960s, they knew the universe is expanding. So they said, okay, it's expanding. It's getting less dense because it's expanding. So it gets less stuff expanding. So you get less stuff in a sphere. So they said, okay, let's just postulate that basically there's spontaneous creation of matter that like fills in for the decreasing density. Okay, so you have a universe that is expanding, but it's not changing because you constantly create random amounts of matter in order to keep it at constant density. Okay? And it turns out you don't need very much. You need something like a proton per solar system per second. Okay? Something we can easily fit with just the local observations. It turns out that this theory was quite popular in the 60s, but it was killed by discovery of the closing microwave background, which we now, it's a verification from the early universe, from kind of 300,000 of the Big Bang. And we know this is the wrong story, but in principle it's kind of physically a bad story. So now we know that the universe is not infinitely old, and it's also not constant. So very often you can just write a very nice theoretical physics theory that's kind of symmetric in all possible parameters, but just go, right? So this is one thing. Universe is symmetric in space, but not in symmetric time. It's changing. Okay? So now that I'm giving all this spiel in my hands, and I'm just asking, is the past going to answer the actual question? What was there before the Big Bang? And the short answer is that I don't know. The slightly longer answer is that I don't think anybody knows. Okay? But to give you a slightly more satisfying answer is that the way we do this physics is we always take time forward. So we know how the physics works around us today. Okay? So if you extrapolate back in time, we know the universe gets denser and smaller and hotter. Okay? And as you keep running the clock backwards, the universe gets denser and denser and hotter until you reach, let's just say, if I extrapolate to time equals 0, I get this point of infinite density and infinite temperature. Okay? But the point is that infinities never are real. So infinities always exist as a mathematical concept, which in physics tells you that you reach the limitation of your theory. Okay? So when you get infinities in your theory, which is at the point of Big Bang, which means that your theory breaks down and it's just incomplete. You need something else like this. But in fact, we know the theory breaks before infinite densities. So as you go to earlier point in time, we reach the regime when energies are so high and they're so large, and we know that simply the present physics cannot explain it. It's wrong. We don't have a consistent theory to link quantum mechanics with gravity. We simply cannot write it out. So we know, we at least we don't know, and this is something like 10 to the minus 30 seconds, like 0.0030 times 1 seconds after Big Bang. And until we write this theory, there is no given point to speculate what it is, right? So we need to understand physics better. We need to unify quantum theory and gravity to even try to approach this question. And then I will be able to tell you. So try to tell you.
That was 5 fantastic 12 or so minute talks from 5 astronomers. And actually, there are far more than 5 astronomers in this room right now. I know they have a pretty busy day tomorrow, but there are several around here. So if you see someone who looks at all like an astronomer, feel free to ask them some questions. They don't all look like astronomers. There's at least one guy here wearing a shirt that says nerd on it, who's definitely an astronomer. There's a table over here, a table over there, and a few around. around. So if they are willing to stay around, buy the beer, ask some questions, and keep talking about astronomy. Thank you so much for coming out tonight.